In this module, we will discuss transport through one-dimensional systems. We will discuss the transport mechanism by taking quantum point contact as the candidate device. Then we will discuss conductance quantization. We'll move on to another similar device called atomic point contacts, and we'll also discuss the applications of these devices. Okay. So these quantum point contacts are one-dimensional ballistic constructions. What you have here is a thin construction where the transport is one-dimensional. Usually, these devices are realized on a two-dimensional system, on a two-dimensional platform. So you have the three-dimensional system, then you go to the one-dimensional by various technologies that we have discussed, such as semiconductor heterostructure or two-dimensional layered materials or whatever you have. You remove one dimension from 3D, you go two-dimension. Now the next step is you remove one more dimension, then you will get a one-dimensional system. Okay, so you start with a two-dimensional semiconductor heterostructure, which we have discussed in one of the previous lecture. Then you realize a thin one-dimensional channel in the middle by the technique electrostatic gating. That also we have discussed in detail. So you have a semiconductor heterostructure. It could be gallium arsenide, aluminum gallium arsenide based, or silicon germanium based, or you can also have a two-dimensional electron system based on the layered materials such as graphene or any other van der Waals semiconductor. So your starting point is a two-dimensional system. What that means is the transport in the vertical direction, where I have assumed is the direction is forbidden, or it's a perfect two-dimensional system. Now, before you apply these gate voltages, the transport happens freely in the XY plane. It is a free electron gas, free electron quantum gas in the XY plane. Okay. Now, once you apply voltages to these surface gates, you are going to realize a thin channel electrostatically. The technique which we have discussed in great detail in one of the previous lectures. So, the x direction that is along this constriction, the electrons can still move, but along the y direction, there is a confinement which is nearly parabolic. May not be a perfect parabola, but you can approximate it to a parabola, which is pretty close to the practical situations as you see the data in the coming slides. Okay. So you have y direction a parabolic confinement. That means quantizing energies. Now x direction is free to move. Is the direction it cannot move. Okay. Now the illustration here shows roughly how the potential energy landscape is going to look once you have all these voltages turned on. The energy of the electron is given by the energy in the y direction, that is the quantized energy of a parabolic well, then the free particle energy along the x direction. So what you have is This is the energy along the y direction, and this is the energy because of the motion along the x direction. This is energy due to the confinement in the y direction. And this is the total energy. Okay. Now, what you have is you have a series of one-dimensional subbands or modes in the channel with roughly spaced in energy approximately 1 electron volt apart, but these all depend on various parameters. Okay, how close the gates are, what is the carrier concentration, all there are finer details to it, but you can think it's something like a milli electron volt. And we probe the system close to the Fermi level. Here we are always sitting in the linear transport regime where your charge carriers are moving on the Fermi surface or very close to Fermi surface within the temperature broadening. So what you have is you have the modes along the y direction because of the confinement. If I draw it here, so you have this confinement because of the voltage on the gate, then the electron wave functional form modes in the constriction. It's the first mode, then you can have second mode and so on. Okay. So the number of modes roughly is given by 2W divided by lambda f, where lambda f is the Fermi wavelength or de Broglie wavelength of the electron. So you will have this many number of modes in the constriction with a given width. Okay, to start with. But now you can change the width by applying the by varying the voltages on these gates. So when you increase the negative voltage, or when you reduce the voltage, make it more negative, then the electric field will creep more into the channel and eventually it will close the channel also. So that is the effect that we are going to look. So the width of the channel you can control, and this now what that means is the number of modes also you can control, which is available near the Fermi level, because you have to understand that the transport always happening at the Fermi level. So at Fermi level, how many modes are there? Okay, then your transport or conduction will depend on that. And the energy scales here are the temperature broadening and the subband spacing. So the subband spacing is of the order of milli electron volt. What that means is, to observe this effect, you need low temperature. Okay, it's not just the subband spacing, it's also the system also need to be in the ballistic transport regime where the electron doesn't undergo any collision. What that means, the mean free path of the electron should be much larger than the dimension or the length of the channel and the width of the channel, or width and length of the constriction. So if you factor in all these and also the one-dimensional, also the subband spacing of the heterostructure or the interface or the two-dimensional electron system, what you can understand is what you need is a low temperature environment to carry out these experiments or to observe this effect. Okay, so this is a cryogenic transport experiment, whatever you are going to do. Okay, all right. Now let's look at the energy levels along the constriction. Okay. So what you have is a constriction, not just a constriction, you also have a saddle point in the middle of the constriction. So this is the x direction. That's the direction the electrons are going to move through the constriction. That is this direction here, x direction. Because of the electric field, the bottom of the well is not as low as the energy of the two-dimensional electron system, which is further. So you have a small bump as the electron pass through the constriction. That bump is created by the voltages on the gate. Okay. So as the electron moves along this direction, this is what the energy is going to look like. Okay, this is how the energy levels are going to change. And these splitting that is shown here, these splitting are available only at the constriction. Far away from the constriction, you have a two-dimensional system, and all these levels will actually collapse onto the two-dimensional, whatever the energy of the two-dimensional electron system. So as it approaches the constriction, it's going to start feeling the confinement effect of the due to the gate along the y direction. Then suddenly this will split into the one-dimensional subbands whose energy is given in the previous slide. So you have a parabolic confinement as shown at the constriction. Not only that, you also have a saddle shape potential. Okay, and this is along the y direction. So now let's look at the transport through the system as a function of the gate voltage. That is one of the main control or knob that we have. Okay. So as you vary the gate voltage, as you make the gate voltage more and more negative, you are going to increase the energy of the electron at the constriction, and you're also going to make the constriction more tighter. So you have two effects. Number one, you will change the base of this parabola because the negative voltage will increase the overall energy of the parabola, or energy of all the levels. Number one. Number two, it also makes the parabola more tighter or more sharper, more acute. So when you push the parabola up, you will push the levels gradually up with respect to the Fermi energy that is shown here. So the number of levels or the subbands in the channel in the channel available for transport depends on the gate voltage. So if you increase the gate voltage, so if you when I say increase, if you when you make the gate voltage negative, you will push the parabola up and the levels will escape one by one. So you will have fewer and fewer levels or channels for transport. That is one effect. Second effect is when you reduce the gate voltage, when you make the parabola more tighter, acute, then the subband spacing also will increase. That also will cause the energy levels to go further apart. That also will add to the DC shift the parabola is going to feel. There are two effects, but both effects will cause the energy levels to go beyond the Fermi energy, beyond which it cannot carry any electron, that level. Okay, that state is not available for transport. So when you vary the gate voltage, you will sweep these levels across the Fermi level and one by one, so that you will have lower and lower number of channels available for transport. The number of channels available for transport will reduce, in an integer fashion, and that's going to cause a step-like behavior in conductance, in the reduction of conductance. So if I plot the gate voltage as a function of, so if I plot the conductance as a function of the gate voltage, if it is the usual field effect device like a FET, then you are going to see a smooth reduction of conductance. It is the usual field effect device, right? But in this case, what you have, you also have a small gap. That gap is going to create a channel, and the electron energy is condensed in the channel. So when you sweep the gate voltage, you will basically change the number of levels available for transport in a step-like manner, and you will see that in the change in the conductance or current also. And from the Landover formalism, which we will discuss in very detail in one of the next class, but now you have to take it for my word. You have to take my word for it. Okay. So the Landover formalism is telling you that the transport in one dimension is the conductance in one dimension is given by E square by H, that is the conductance quantum, okay, quantized conductance, into the number of channels. When I say N here, what that means, the number of channel, one number of reflectionless channel. That means there is no reflection or backscattering in that channel. Okay, and we have also defined that this device performs in the ballistic transport regime. What that means is the dimension of this constriction is far small, compared to much smaller than the mean free path. So you don't need to worry about any reflection inside the, or reflection or scattering inside the channel. Okay. So as per Landau formalism, what we have is the conductance should go in a step-like manner with the number of channels. And as you vary the gate voltage, you are reducing the number of channels and you are reducing the conductance step-like manner. And you can see from this plot or any of these plots here that it is going to be like the conductance is going to vary in a step-like manner and in units of E square by H. That's what you are seeing. And these two are two of the first experiment. Both happened in the same time period, 1988. These are the first two papers where they have observed the conductance. Okay, first reports of this quantum point contacts. Okay. Here, one thing which you need to be aware of is the conductance is varying not in E square by H, but 2E square by H. Okay, it is 1, 2, 3, 4, and so on. Okay, it's going to vary in 2E square by H conductance. Okay, but that again depends on whether you have spin degeneracy or not. In the absence of any applied magnetic field, you have both spin up and down going through a channel. So every quantized channel corresponds to 2 spin channels. So this N will be 2N, or you can say 2E square by H instead of E square by H. That is what you are seeing here. But if you apply magnetic field, then what you're going to have is you will see the effect of spin. Because spin is another channel. Okay. So as shown here, you have zero field, you have, it is quantized in 2e square by h. The moment you vary the field and the high field, you can see that each of these is going to split into 2. So you have e square by h steps. But in the absence of the field, you have 2e square by h step. Okay. And any other degeneracy is going to provide additional channels such as valley. This is from a graphene, bilayer graphene quantum point contact, where you have a thin sheet, 2 layers of carbon atoms, okay, BLG, bilayer graphene, which is sandwiched between two insulating two-dimensional system, that is HBN, hexagonal boron nitride. And the details you can, how to make this device and other details of the measurement you can find in this paper. But the take-home message here is, here you can see that these are 4e square by h steps, because there are 4 channels for the system. Every quantum channel correspond to is 4-fold degenerate. Okay, what that means, you have 4e square by h. And you can see the moment you apply a magnetic field, you lift all this degeneracy and it's going to be eventually e square by h. You can see that it's split into e square by h. Each of this plateau is split into 4 individual plateaus when you take the field from 0 Tesla to 5 Tesla. Okay. So every channel, when I say channel, every reflectionless one-dimensional channel, every ballistic reflectionless channel, okay, is giving you e square by h for conduction. That is the resistance of the channel, and that is given by Landauer formalism, which we will discuss in detail. Okay, so that is the take-home message from these 2 slides. So if you have spin, then you will have degeneracy 2. Then if you have valley, then you multiply spin and valley. Then you have that many states. In this case, it is 4-fold. You have 2 spin, 2 valley. Okay, that's what the story so far. Okay. Now there is the very famous work by a group in Harvard headed by Bob Westervelt, and which is published in this article here, where they have imaged the coherent flow of electrons through this constriction. So what they have done is, they have a 2-dimensional electron system. A cartoon of the setup is here, and you have a gate which scans over the sample. It's a moving gate, which is a AFM tip, which you can bias and you can use as a gate, but it also moves across the sample. Okay. So in addition to these 2 gates, you have one more gate, but you don't apply a lot of voltage on this gate. That is not the idea. The idea here is, you have this one-dimensional channel which looks like a coherent flow of electrons through the channel, and you want to sense it. Are there modes? Because the theory says there are modes. Can we visualize it? Can we see those modes? Okay. So what they have done is, they measured the transport through this device, and without this tip, they just got this step-like behavior. Now what they did is, they parked on these plateaus, for example, first plateau, second and third, and so on. And the first plateau should have only one mode going through it. So when they scan the tip over the sample, okay, whenever the tip is on top of one of these modes, then because of the field of the field due to tip, the transport to the channel will get affected, and that they somehow decode and plot it. So what you can see here is whenever the tip is far away from the center, you don't have any change. What they have plotted here is a delta G, the change with respect to tip. Okay, whether you have tip there or you don't have tip there, it's a change in the current through system. Now we can see that whenever the tip is far away, if you have a single mode, that should be propagating close to center. Okay, so when you are far away from the center of the constriction, you don't have any effect. But when you reach near the constriction, okay, I can assume I can just interpolate these channels here. Okay, then you have effect. You can see that delta G here is actually substantial. Delta G plotted here is the change in the current. Because the tip is going to dent the wave function, or you can poke on it, and that is going to have an effect on the transport through system. Okay, you can simply think that it's going to affect the ballistic transport, because it's going to provide a scattering center for the electron. But when it is too far from the center, electrons are really not going there, because they are going to the center in the first plateau. Now, when you go to the second plateau, they actually have seen two modes. That's what they have. You can see two modes. And when you go to third plateau, you can see three modes. Okay, you can see three of them. So this is such a beautiful experiment where you can directly visualize this quantization and these modes of the electron going through this constriction just by scanning the tip over it and measuring the current. But it's a very interesting and also involved experiment, but it's very easy to understand. So what we are seeing here is the plateau, this quantum point contact is acting like a waveguide, similar to a waveguide for electromagnetic waves for electrons. So electrons going through this constriction will have its wave nature, but because of the boundary condition created by the gate, because of the boundary, the wave function should go to zero. Okay, it's going to propagate through the constriction like the waves, electromagnetic waves going through a waveguide. So you can think that quantum point contact is like a waveguide, similar to a waveguide for electromagnetic waves for electrons. Okay. Now, this quantization is not just a phenomena which is restricted to these two-dimensional electron systems. You can see similar effects in conduction, other constrained devices too. One of the most studied system is an atomic point contact. Okay, so what we have is an atomic point contact. Atomic point contact, or people also call it APC. APC. Okay. So what you need is quantized number of modes through the conductor. That's all your condition, and every mode, which we assume it's reflectionless, is going to contribute E square by H. That's all the physics says. It doesn't talk about gates, it doesn't talk about two-dimensional electron system, nothing. You just need quantized modes. That's all it is. So for metals, to observe these quantized modes, you need to have your Fermi wavelength, which is also size of the dimension of the conductor. The Fermi wavelength for semiconducting systems, such as the two-dimensional electron system, is pretty large, because the Fermi wavelength is lambda f is basically goes up as the carrier concentration goes down. This is n carrier concentration. Okay, is 1 by n. This term here is. So for metals, the carrier concentration is very, very high. The lambda f is of the order of the interatomic distance or interatomic scale. So what that means is, to observe this effect, you need to have the device dimension comparable to lambda f or smaller. Then only you can see the condensation effects. And for metals, what that means is these should be of the order of interatomic spacing. So you cannot see this condensation of transport in metals in the similar size scale as that of the semiconductor. You need to go to atom-atom point contact, okay? Because your constriction should be like of the dimension of lattice constant, okay? So the way that we achieve this is taking a conductor and pulling it or bending it, and to a point where the constriction is made by a contact between few atoms, okay, and eventually you break it, then you're done, okay. So you can pull a thinned conductor here. For example, you can take it's shown here also. You can take a nanowire, then you etch it down and make a really neck-shaped region in the middle. Then you pull it or bend it such that the last few moments you will have the contact is broken atom by atom. Okay. So when you do that, what you are going to see is a step-like behavior in transport. So that's what is plotted here. You can see the transport or current goes down, or conductance goes down in G0. G0 is again E square by H. But here it is plotted as a function of time. The time is basically time of bending or time of pulling. Similar behavior is observed in another system too. Okay. So these devices are called atomic point contacts, and here you can see this condensing effect even at room temperature. You don't need a really low temperature environment because the energy scales involved are pretty high in this case, because you are talking about breaking or making connection between two atoms. Atom-atom connection is one channel. When you have two atoms connected, it's two channels, like, and so on. Okay. So the action of you breaking or pulling this wire is breaking the connection between the two sides, atom by atom. Okay. And every one of those is going to give you a step in the transport. So that is the technology and physics of atomic point contact, or in short, APC. But this condensation effect is something universal in conductance. It doesn't care about whether it is a semiconductor or a metal or anything. All it says is, all it depends is on the number of modes available for transport, and each mode is going to give you E square by H in conduction. Okay. Now, very interestingly, you can also see condensed transmission of light too. So there is a landmark experiment is published in this journal. What you have is, you have a source of light. Of course, you have a diffuser, which is going to make it uniform. Then you have something like a detector, which is in the form of a sphere here. And you have some arrangement to basically control the width of this opening through which the light is entering. This is like the electrons going through the constriction. The light is going into a region where you can measure the intensity, which is an integrating sphere, through a collimator whose width you can control. Okay, by a piezo. And what they have measured is again the transmitted power, which is collected here, varies a step-like manner as a function of slit width, which is exactly what we were also saying for the case of quantum point contact or atomic point contact. So this quantized behavior of transmission of light or transport of electrons basically depends only on the wave nature of electron and the quantization condition in the constriction. And this is the beauty of the quantum behavior of electrons or photons. Okay. In the next lecture, what we will do is we will look into the details of the one-dimensional transport and the Landauer formalism.